Okay, in this presentation we are going to look at random number generation. So essentially the exercise here is to simulate some random variables that are drawn from certain probability distributions. Okay, so we start off here with this set of values here. So let me read that out. The following values are a random sample from a uniform probability distribution on the range of 0 to 1. So we have 0.209, 0.363, 0.516, and 0.970. Okay, now they just happen to be in order, but that's not really relevant. Now, just as a quick remark, that when you get more familiar with computer science and statistics and so on, and statistical computing, you realize that the values drawn from a uniform random variables or random numbers are straightforward matter. Okay, so essentially they're the building blocks for random number generation for other probability distributions, because in that instance it is an extremely straightforward matter. Okay, for the uniform distribution. So anyway, exercise A, use these values to generate 4 random variables from the standard normal distribution, explaining your method carefully and give your answers to 2 decimal places. Use the results from exercise A to generate 4 random variables from the chi-square distribution with 1 degree of freedom. And then, finally, C, use the results of exercise B to generate 1 random variate from the chi-square distribution with 4 degrees of freedom. Okay. Now, essentially, there's a little bit of a sort of a thought process here. So this actually shows how random numbers are created for various probability distributions, specifically the chi-squared here, but essentially just actually shows the workflow from a raw source, which is uniform probability distribution, to something that is, let's say, complex but applicable, which is, let's say, the chi-square distribution. Okay, now, so anyway, let's get started. Exercise A, generate random variates from the standard normal distribution. Okay, so to generate random variables from the standard normal distribution with mean 0 and standard deviation 1 using uniform random samples, we use the inverse transform method. So this involves using the cumulative distribution function of the standard normal distribution. In fact, the inverse of it, really. So what we can do here is we convert to uniform samples to the standard normal variates. We use the inverse of the standard normal cumulative distribution function, also known as the quantile function or the Probabilty function. Okay, so let's start off here. We have our sample here. U equals, U being obviously that they're uniform. They have a uniform distribution. 0.209, 0.363, 0.516, and 0.970. Okay, that's just the numbers that we started off with. So what we're going to do is apply the inverse cumulative distribution function, the Probabilty function. Okay, now essentially this is actually very similar to working with the standard normal distribution statistical tables. Okay, but essentially it's sort of like going in reverse. We're sort of it's actually when we have the z-score and find the probability, this is actually sort of just going in reverse, really. If you're familiar with the standard normal distribution and normal distribution and worked exercises and statistical tables and Murdoch-Barnes and stuff like that, this is essentially what we're doing, is working in reverse. So we're starting with the probability, which is what an analog of 0 to 1 is, or it's an analog of probability, and then just finding the z-score. That's essentially it in a nutshell. Okay, so anyway, let's continue on. So Zi, that is the variate, the standard normal variate that we want. That is the inverse cumulative distribution function, phi to the minus 1 of ui. Okay, so essentially what we do here is get phi I is the inverse cumulative distribution function of the standard normal distribution. Okay, so essentially phi to the minus 1 of 0.209 is approximately equal to minus 0.81. Okay, so if let's just say you're looking at a z-score and your z-score is 0.81, that should give a probability of 0.209 or minus 0.209. Okay, or that's what you should be working out if your z-score is minus 0.081, okay? Likewise, if your z-score is minus 0.35, you should be looking at a probability of 0.363, okay? So essentially, we're just working in reverse here, okay? Anyway, I digress. So let's just look at the answers here. 5 to the minus 1 of 0.209, that is approximately equal to minus 0.81. 5 to the minus 1 of 0.363, that is approximately equal to minus 0.35. 5 to the minus 1 of 0.516, that is 0.04. And 5 to the minus 1 of 0.970, that is approximately equal to 1.88. Okay. Just as a quick remark, you notice that the univariate, the uniform variates less than 0.5 equate to a negative number, and the ones that greater than 0.5 correspond to a positive number. And again, that's just related. That sort of essentially chimes with the normal distribution. Anyway, so the generated standard normal variates are approximately minus 0.81, minus 0.353, 0.04, and 1.88. Okay, I better hurry up. So what we're going to do now is generate random variates from the chi-square distribution with 1 degree of freedom. Okay, so the chi-square distribution with 1 degree of freedom is the distribution of the square of the standard normal variate. So essentially what we have to do here is just get the values from exercise A and square them. Okay, so the first one is minus 0.81 squared, that's approximately 0.66. Minus 0.35 squared, that is approximately 0.12. 0.04 squared, 0.00 essentially. We're just told to go to 2 decimal places if you recall. And 1.88 squared, that is approximately 3.53. Okay, so that's our list of chi-squared random variables with 1 degree of freedom: 0.66, 0.12, 0.00, and 3.53. Okay, so that's it there. Chi-square distribution with 1 degree of freedom is the square of a standard normal variate. Now, generate a random variate from the chi-square distribution with 4 degrees of freedom. Okay, note that 4, it's not there by accident. The chi-square distribution with 4 degrees of freedom is the sum of 4 independent chi-square variates, each with 1 degree of freedom. Okay, so essentially what we have to do here, if we want a chi-squared random variate with 4 degrees of freedom, essentially what we can do to generate one is add up 4 chi-squared variates that have 1 degree of freedom, which we have got from exercise B. So one variate is the sum of 4 variates with 1 degree of freedom: 0.66, 0.12, 0.00, plus 3.53. So that gives us 4.31 approximately. Okay, so the generated chi-squared variate with 4 degrees of freedom is approximately 4.31. Okay, so that's the general gist of it, and yeah, that's it really. So essentially just actually understanding how these distributions relate to each other. Okay, and the inverse transform method. So there's a lot to work with there. Okay, we'll leave it there.